And welcome to SanfordFlipMath, the home edition. This is pre-calculus. We are in section 1.2 of the Larson Battaglia book. We are now talking about functions. What are functions? Starting the vocabulary about functions. Chapter 1 lays the groundwork for the work that we're going to be doing for the whole book. Talking about, first of all, vocab and things like that. So I guess we'll just hop right into it. Most of this should be review again, much like section 1, just a little more technical and a little more pre-calc focused. So first we're going to start out with some definitions. So just a reminder that a function is a relation. A relation is any, dare I say the word again, relationship. A relation is any connection between two sets of numbers. Typically, we think of those labeled X and Y, whereas a function is a specific kind of relation where every input variable or X variable or independent variable, or sometimes it's not X, but any input variable is paired with exactly one output, which is the Y variable or dependent variable. Let's just look at some quick examples. So sometimes we look at these in terms of sets of numbers. So we might have an ordered pair of 1, 3, and another ordered pair of 2, 7, and another ordered pair of 5, 15. Okay, so notice that this X value of 1 only has a single Y value of 3. Okay, whereas an example that looks like that but doesn't really work is, what if we had 1, 3, and maybe we had 1, 7, and maybe we could still have 5, 15, right? So let's see how, so the idea is when I put in the 1 as an input, how do I decide which of these X values or which of these Y values are the correct answer for that? So this is considered not a function. Okay. Sometimes you'll see this in a cloud of numbers. So like I might have this listed as, 3, 15, and 5, and these are the X values. Over here are the Y values, and it could be 10, 17, and 6, and they don't have to be in any particular order. And maybe I do something like this and something like that, right? So I have little arrows showing that the 3 is paired with a 17. So that would be the completely equivalent to this, right? That X value and that Y value are connected together. Okay, whereas again, if we had the same kind of thing, I might have, here's my X and here's my Y, and 3 has an output of 1. Oh, look, 3 has an output of 2, and 3 even has an output of 3. So this is not a function. Okay, so I'm trying to do, here's an example, here's a counterexample or a non-example. Okay, sorry if that was out of focus. Okay, let's do 2 more with equations and then graphs. So equation, maybe we have y equals 3x squared plus 5. Now, no matter what X value I put in, I'm only going to get a single answer. Now, it is probably worth noting that, so here's an example. So if I put in the number 1 squared is 1, times 3 is 3, plus 5 is 8. Okay, we're following the order of operations. Also worth noting, if I put in -1, -1 squared is 1, times 3 is still 3, plus 5 is still 8. Now, don't freak out. This is still a function because this input of 1 has a single output. This input of -1 has a single output. I can have the same output with different inputs. That has nothing to do with it. It's all about, does the input have a single output? So here is the opposite situation. So for instance, I might have something like that. So here I'm going to put in, let's put in 3 because it'll work out kind of nice. 3 plus 1 is 4, square root of 4 is 2. But I have that plus or minus there. So worth noting, this really represents 3, 2, 3, -2. This is not a function. Okay. Okay, let me just do one more of this, and then we got to circle back and do another couple vocab words that, again, you should know. Okay, so what if I had a graph that looked like this? Now, many of you are going to remember something called the vertical line test. And the vertical line test is to test if something is a function. And with the vertical line test, a vertical line, which represents an x value, can only touch the graph in one point. So in other words, if I pass a vertical line across this graph, so here is a vertical, I'm gonna try and keep, or here is a ruler, I'm gonna try and keep it vertical so you can see it like a line, right? So if I pass this across, so it's only touching the graph in 1 point, 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 1 point. So these every time I stop, that is representing an x and a y value right wherever it's touching, right? So here's an x and a y value here. Here's it. So for every one of these x values represented by this ruler going across, right? It's just it's my favorite SpongeBob ruler, sorry. Then I'm only getting one y value out of it, okay? All right, so here is a possible situation where it's not that. So here's like the inverse or something that looks kind of like the inverse of that. So worth noting that if I cross this, a vertical line across this thing, okay, then I'm actually touching this in two places when I do that. So here's like a specific vertical line. And again, a vertical line represents an x value, right? Remember, vertical lines are x equals something. So this like could be x equals 5 or something, I don't know. And maybe this y value is 3, and maybe this y value is -3, perhaps. So that one x value, 5, has 3, but it also has -3. So not a function. Okay, whereas if I have a vertical line through this guy, it only touches at 1 point. Okay, so also something that goes with the functions, what a function, things like that, any kind of equation really, is the idea of domain and the idea of range. And I know you've learned about this before. So domain goes with x, it's the input values, and really it is the set of allowed x values. They're the x values that are meaningful. They're the x values that you have been given freedom to use. They are the x values that work. And there are actually two kinds of domains, and we'll talk about those in a hot second. Range is the set of possible outputs, or in other words, the y values. Okay, so for instance, if I pop back over here to this guy, the domain of this is all real numbers, which I'm going to let you write a fancy R if you want, or you can write the words all real numbers. Or you could even write x between -infinity and infinity. Seems like more work to me, but you are welcome to do that. Or there is such a thing called interval notation. I know this is going to look like an ordered pair, but it's really not. This is saying the x values between -infinity to infinity. So these are all different ways to say all real numbers, or in other words, you can put anything into this guy. Okay, now the things that can come out of this though are not everything. If I did a graph of it, it would actually look kind of like this. This parabola has a bottom to it, and the only y values from this equation are going to be greater than 5. Okay, so if we did the range, we could say, okay, so notice this had like a double vertical for reals. This range does not. So range, I could say y is greater than or equal to 5. Or in interval notation, it looks like that ordered pair kind of thing, only if you're doing an or equals, you put a bracket, but infinity, we can never actually get to infinity, so we put a parentheses for that. So here's a quick example of domain and range. So domain, what x values are you allowed to put in? Well, in this thing, you're allowed to put in anything. Range, what kind of y values can you get? Well, for this thing, it's just stuff bigger than 5. Okay, usually for most people, the range is the trickier because you have to kind of know about what the function is going to do as opposed to just knowing the limitations. Okay, so let me talk for a little bit about domain and range specifically. Okay, so domain, as we said, was the set of all allowed x values. Sometimes they tell you what you're allowed to use. So this is especially true for piecewise functions, but it's true otherwise. So like for instance, if you're allowed to do something on the clock, between times from 3 to 5 or something like that. So that could be a potential explicit domain. Okay, or maybe I want to know the range values, and I just straight up tell you some ordered pairs. So like I want, you could give a function in a table format, and I might say specifically, I want the y values when x is -1, 1, and let's say 2, right? So then you're going to put those in and find the range or something like that. So it can be explicitly stated. They tell you the exact values or a range of values. They might say, go from, for x values bigger than or equal to 3. So that's fine. Okay. Sometimes the domain is implied by what works in a function. Okay, so in other words, you can't take the square root of a negative number without getting weirdness, like imaginary numbers, right? So if I had something like y equals the square root of x, well, the domain would be only x's that are greater than or equal to 0, or the non-negatives, you could say. Okay, or if you were doing interval notation, you'd say 0 to infinity. Okay, so this is implied by the kind of equation it is. The limitations of this. So we don't know how to do a square root of a negative number without getting into weirdness. Okay. Range is a little trickier because you have to know stuff about the function. Like for instance, I know that this function, I'm only allowed, or I'm always going to get a positive answer unless there's a plus or a minus here, right? If there's a plus or minus here, then that's going to change things. Or I need to know about the shape of the graph. So this particular graph, I happen to know this is a parent function, a basic function. So it's going to look like this. And again, this is none of this should be new stuff for you. We're just kind of nailing it down because we're going to be using these words a lot all of this year. So you need to own this. There is going to be an expectation that you know what's going on here. Okay, so for the range for this guy, we're going to say y is greater than or equal to 0. So the domain happened to be x greater than or equal to 0. So things to the right of 0 and including 0. And the range is the y values greater than or equal to 0 because it goes above and touches the x-axis and then it goes above. So those are the y values that are present there. Okay, so we're going to do that for these guys, and I'm going to kind of keep moving because the section has a few things in it, and again, none of this is new. But you are very welcome to pause or rewind. You're in charge of the little slider. Sometimes it's helpful to think about the graph. So like for instance, this guy, because it doesn't have an exponent here, is linear. It's a line with a y-intercept of 4 and a slope of 3. So it's going to look like this. So are there any numbers that you can't multiply by 3? And then that answer that you can't add 4 to? And the graph is a hint. Remember, domain is about x's, and so we're thinking about left and right. There are no jumps, bumps, funkiness, points skipped, or anything like that left to right. So the domain for this thing is all real numbers. Okay, it does go forever up, forever down, and there's nothing skipped, there's nothing missed. So the range is all real numbers. Okay, so everything for this is going to be about like what's the shape of the graph look like, and then we interpret the other stuff we're talking about. So right now we're not giving you any explicit domain or range, so we're trying to figure out what you're almost never given an explicit range, but sometimes an explicit domain. But most of the time we're looking for the implied domain, the things that, because you can't divide by 0 because you can't take the square root of a negative, those are the things that we have a problem with. Okay, so this is a parabola because it's x squared. Okay, so you should know that. And because of the -4, that actually moves it down. And we'll talk about the whole shifting and all that stuff again, so we can reinforce that. So as you're thinking about this, left and right, there's nothing skipped. I can square any number in the universe and then subtract 4 from it. So there are no limitations on the domain. Okay, so there's my funky R. But notice that the graph only goes down to -4. It doesn't go below that. So now I need to say things like above and including -4. So I can say, now this is range is about y, so I'm going to use y greater than or equal to -4. Again, you are welcome to use interval notation. Oh, sorry, that was a biff. And so that means from -4 up to infinity. And again, infinity, We use the bracket when it's included, like it would be a less than or equal to or greater than or equal to. Okay, but we use a parentheses with infinity always because it's impossible to get to infinity. All right, now I'm being a little mean to you on this next one. So you could play with this on your calculator. I'm sure you aren't going to be able to, well, I'd be shocked if you could just look at that equation and know what it is. Okay. Now, the other issue with the calculator is if you don't have your window set in such a way, you might not see exactly where this thing does stuff. And that's tricky. So I am a big fan on the TI-84 of zoom decimal because it will actually hit points like these two. And if you just do like a zoom standard, it does some weird decimal-y stuff on the pixels of the screen. So you might not get, it may not look like it connects, but this is actually a semicircle and it touches at -2 and at +2 and it goes between them. Now you could probably think that through in your head by looking at this and saying, well, if I put in 2 squared is 2 and 4 minus 2 is 0, and I can do the square root of 0, so that's okay. Or I could put in 1, 4 minus 1 squared is 3, so that'll be 3 square root of 3. Okay, it's ugly, but it's a valid number, 1.732. But if I put in 6 squared is 36, 4 minus 36, -32, square root of -32, negative 32. What? Wait a minute. Yeah, you can't do that. So the graph can be a hint, but the idea is you can't take the square root of a negative, again, without imaginary numbers, which have their place, but that's not usually what we're talking about. So the domain of this thing actually end up going from -2 less than or equal to x less than or equal to 2. Now, here's a pro tip. When I do this combined notation like this, where I'm really doing two inequalities at a time, the variable always goes in the middle. These two letters or these two symbols have to go the same direction. So if it's less than, they both have to be less than. Now, me personally, I always do less than because I want to go from small to big. And -2 is not bigger than 2. So these two guys always have to go the same direction. If they're not going the same direction, then you're doing something wrong. This only works when you're talking about values between. And again, if you wanted to use interval notation, you would write it like this. I don't care which one of these you use, but you need to know what you're doing. And I do not like mixing and matching. So I just think it's tacky. So if you're going to use inequality notation, then use inequality notation. If you're going to use interval notation, then use interval notation. And now you could mix and match between number 1, number 2, number 3. I don't care about that, but I'm saying within the same problem. It's just cheesy. It's like putting a decimal in the middle of a fraction. Who does that? Ew. Wearing different socks. All right, that could be a fashion choice. All right, moving. All right, now the range only goes from 0 to 2, 0 to 2, and it does include both. Or if you're going to use the inequality notation, why did I do -0? That is just silly. All right, let's try this again. 0 less than or equal to y less than or equal to 2. There we go. So if you're doing this, do that. If you're doing this, do that. All right, I need to kind of move along here because I know this video is going to get crazy. As we look at this, there is a specific number that you are not allowed to divide by. That number is 0. And we can talk about why that's true if you wish, but I'm just going to leave it at that for now. Well, what is the x value that would make that 0? Well, x can't be that number. So it is a restricted value. It is not part of the domain. And there are a lot of ways to write this. You could say that for the domain, x can't be 3. Now, there are fancier versions of this. You know, in college, they might say you have to write the set of all x such that x is not 3. I don't need you to do that. This is good. So basically what this implies is f can be anything in the universe, but not 3. It is perfectly acceptable to write x less than 3 or x greater than 3, because numbers that are less than 3 or greater than 3 are both acceptable. Okay, and you could do the similar version of this in interval notation, but it's a lot to write. You know, so if you would like, instead of writing the word or, the U symbol means union, and in mathematics, union means either that or that. Okay, so all of those are legit. Now, you might want to play with this on a graph. And if you do graph this, it's going to look something like this. And this has asymptotes. Asymptotes are lines that the graph approaches, but isn't going to touch. And x equals 3 happens to be that vertical line that is a line that this graph approaches and it's not going to touch. And this happens to also have a horizontal asymptote. And I'm about to show you a sneaky little trick that will help you find that. And we'll get some practice. But I'll show it to you on that one, and then we'll circle back and show you how it worked on here. But this graph is actually not going to touch the y-axis. Okay, so the question is, what's the range then? Well, not the y-axis. Well, y-axis is not a number, but you're going to say y is not 0. Or you could write it like any of those other ways, right? All right, so this particular one, the domain starts out the same. X can't be 4 because you can't make the denominator 0. Okay, if you were to graph this, if I go to x equals 4, well, it turns out that the horizontal asymptote is actually up at 2. Okay, and so -4, so I'm just going to kind of sketch that bad boy in. Okay, so y not equal to 2. Now the question is, how did I know that? Okay, it turns out as x goes way, way, way to the right, as these points go way, way, way to the right, these two terms take over, and the +1 doesn't mean so much, and the -4 doesn't mean so much. Like when x is 1,000,000, this is going to be 2,000,001, about 2 million, and this is going to be 2 million minus, I'm sorry, 1,000,000 minus 4, about 1,000,000, and about 2 million divided by about 1 million is going to be 2. So the bigger x is, either in the positive direction or the negative direction, the less this means. And that's what happens with a horizontal asymptote, is it's all about those matching up the highest degree term. So y not equal to 2 is the horizontal asymptote. It is the value that y can't be. Okay, now, so I told you I'd circle back to this one. So notice how I matched the 2x and the x. Well, in this one, I'm going to match the x with the x in the top. Well, you're probably saying to yourself, there is no x in the top. So I'm going to just write a little 0x in here. And if I match up the 0x and the 1x, guess what 0x divided by x is? The x's divide out, that's 0 over 1, that's 0. Hey, look, that's my horizontal asymptote. That is the restricted value for the range, okay? All right, I got one more little topic to show you. Okay, so pause there if you need to write some of that down. And it's quick, and you know, all of this has been quick. Most of this you're familiar with, some of it maybe more than others. I just want to remind you about function notation, or sometimes referred to as f of x notation. F of x notation is, that's like so basically what you have here is a name. So like I'm going to call this function f, and its independent variable, the variable that is the x variable, is going to be x. Isn't that clever? So if I have like 3x plus 2, okay, great. So f of x is 3x plus 2. And now I can use its name and tell you x values to calculate. For instance, if I say f of 1, then that just means you're going to replace the x with whatever the x is replaced with. So x here was replaced with 1, so you put in a 1. And again, you always have to follow the order of operations. 3 times 1 is 3, plus 2 is 5. Or I might say f of -6. So 3 times -6 plus 2, -18 plus 2, so -14, okay? I could do f of a. Now that seems weird. Well, f of a just means replace x with a. So this is 3 times, oh, I guess whatever that was, plus 2. Now, I don't need parentheses there. I'm just doing it to kind of emphasize the replacement, just like I did here and here. Okay, so if you just want to write 3a plus 2, that's fine. Don't combine the unlike terms, right? Now, one more of these. If I do f of, let's do b plus 2, then that means I'm going to do 3 times whatever that was plus 2. So it was 3x plus 2. So I have to replace that with whatever was in there. And this can get a little tricky, but my advice is replace the x with parentheses and then go back and fill it in. Okay, that's how I would handle that. Okay, and then just a quick little note: if I'm asked or if I'm talking about y as a function of x, then I'm saying y equals something with an x in it. Like this last one, that f of x equals 3x plus 2. If I wrote that y equals 3x plus 2, this is y written as a function of x, meaning it's about x. I'm going to put in x values, okay? Or I might say y equals f of x, which is a way to say it's a function of x. Now, there's nothing magical about the letter f. They just use it a lot, probably because of the word function. But we could talk about, y equals h of t, maybe the height as the time, like you would see in physics or something like that, right? Okay, so if I was doing that, I might say y equals 9.8 t squared plus 20 t plus 1. And so now the height is written as a function of time. Okay, so if I had t equals 3x plus 2, this is not x being written as a function of t, this is t being written as a function of x. Or if I have 2x plus 3y equals 7, this is not y as a function of x. When we say that y as a function of x, the y has to be by itself. So that y has to be alone. So it has to be y equals. And then the x would have to be mixed in the middle of the problem. You could rewrite this as y as a function of x by solving, subtract 2x and then divide by 3. But this is not currently written as a function of x. Okay. All right. So I know that went kind of quick, but again, this is all just us remembering stuff. And maybe we're tightening up some terminology here and there. Remember, you're welcome to go back and rewatch this as much as you want. It'll be here probably for the next 10 years. And again, thank you for popping in to Sanford Flip Math. Well, I didn't want to mute myself. That's me wearing a mask. Okay, not really. V for Vendetta. What a thought-provoking movie. All right, sorry. So if you need, so we'll talk more about this in class as we need to. And thanks for watching Sanford Flip Math. And I guess we are out of here. Bye.